Hi, everyone. So first of all, I'm honored to be presenting this thesis to you. It's funny that this is the first time I'm giving a talk in ICAPS, in the main conference, although I feel very much a part of this community. Ronen was my advisor, and of course this is largely thanks to him. And with that, I'll start. So this is about multi-agent planning. And what is multi-agent planning, at least in the sense that we look at it? We have several agents that are acting in the system and that can affect one another and the system. And the solution we seek is a coordinated plan. Logistics is a nice classical planning benchmark that is naturally multi-agent. And we have packages, we need to move them, and we have trucks and airplanes who are the agents here. So if I leave it at that, there's a very natural criticism that comes and says, well, why not just give this to a regular planner? Why do we need anything special? And that's why we're going to add a difference. And the difference is private information. So we have agents that want to keep some of their information private, and they don't want to share it with other agents. We have some examples here in the slide: subcontractors that don't want to share their private costs, military units, different departments of the same company. The thing is that once we have this private information, this leads to distributed problem solving. So we don't have one entity holding the entire problem. These agents need to solve it in a distributed fashion. And the added bonus is that having these agents can create some problem structure which can help us solve this problem more efficiently. So the focus of the dissertation in one sentence is exploring the problem of privacy-preserving multi-agent planning using simple and expressive models. And breaking this down to high-level objectives, we want to find scalable methods to solve these problems, both satisficing and cost-optimal. We want to go a bit beyond cooperative agents to see what we can do with self-interested agents. And we want to put multi-agent planning on the ICAPS community's radar. So that's the high level, and this goes back, let's say, 6 years. Let's see how we did. So the model we used, I mentioned that we want simple and expressive models, and it was natural for us to choose the multi-agent strips model that is due to Ronen and Carmel's 2008 paper. Essentially, this is a regular strips problem, classical planning, where the actions are partitioned to agents. So each action is associated with exactly one agent. The agents are cooperative, and they don't want to share some of their information. That's where the privacy comes in. So I mentioned privacy. Let's discuss this a little bit and how we formulate it. Once we partition the actions, this induces a distinction of actions and variables to public and private actions. Public are ones that affect and are affected by more than one agent, and private are the ones that are local to a single agent. In logistics, we can consider load and unload public actions, since they can either achieve or destroy other load and unload actions of other agents, and move actions as private because they only change the agent's location variable, and that doesn't affect any other agents except the agent performing the action. So given that distinction, we wanted to find a nice way to take existing benchmarks, single agent benchmarks, and formulate them as privacy-preserving multi-agent benchmarks. And we said, okay, private actions and variables are private information. So that gives us a nice way to take existing benchmarks and formulate them as problems we want to solve. Again, because of this privacy, each agent has only an abstract view of the problem. Okay, so let's see what we tried to do in order to solve this problem. The first thing we tried is a distributed CSP-based approach, and this was related to Ronen and Carmel's paper from 2008. And the intuition here is we want to separate the public and private parts of the problem. For the public part, which is the inter-agent coordination, we want to formulate this as a distributed CSP problem, which makes the solver inherently distributed. And once we have a public skeleton of the plan, which consists of only public actions, each agent can now perform planning with its private actions in order to see if it can support that public skeleton of the plan. So this resulted in Planning First, which was the first fully distributed multi-agent classical planner back in 2010. And it worked well on loosely coupled problems. These are problems where the coordination between agents is not very complex. And this is fits the theoretical results from that 2008 paper. But the fact is that it didn't scale well when coordination becomes more complex, or when the number of agents rises. Another characteristic of it is that its solutions are not cost optimal. They're only locally optimal in the sense that they minimize public actions taken by the agents. So we wanted to try something better and try to scale. And our natural idea was to use forward search, because that's what's working for classical planning anyway. So we wanted to distribute this forward search. And essentially what we did is we wanted the agents to perform best first search with the following changes to the regular methods. First, instead of having a single search space for the entire problem, each agent will have its own search space, where it expands nodes only using its own operators. So we have separate search spaces. Each agent can execute only its operators in their own search space. And relevant nodes are communicated via messages between the agents. And the key observation here is that since we have private actions, and by the way, this relates to the structure I was talking about, since some actions are private, and if I perform a private action, I essentially did not change the way the system as it is viewed by other agents. So we don't need to communicate all relevant states between agents. We can communicate only ones that are the result of public actions being performed. I'll try to give you a very short running example, which will illustrate how this thing works. What you have here on the left-hand side is the action graph. You see two agents, agents 1 and 2. Yellow means private actions, red means public actions. And in the middle, you can see the reachable search space. On the right-hand side, you have agent 1 and agent 2. For each of them, they have their own search space, starting with the same initial state. And now, as I said, we're going to start expanding states using only their own actions. So once we start, we see that agent 2 reaches this orange state. If you look at it in the reachable search space, you see there are applicable actions from that state. But both of those actions belong to agent 1. So this essentially makes this state for agent 2 a dead end. Whereas it is not a dead end in the reachable search space. So agent 1 continues to expand using private actions until it uses a public action, resulting in this red state. This red state is then communicated to agent 2, and from where agent 2 can now continue expanding, reaching the solution. So this very short example shows only one-way communication, but the algorithm supports two-way communication or multiple-way communication. States and their children's states can be moved back and forth between the agents. So the key results from this work are first its scalability. So this multi-agent forward search paradigm outperforms the existing approaches by orders of magnitude for runtime, and it is comparable and even sometimes usually is better in the sense of solution quality as well. The other key result here is that we can have a cost optimal solution if we make some minor changes to this paradigm. The first is we want to use an admissible heuristic, and the second, we need to perform a distributed termination detection procedure, because it's unlike in A star, reaching a solution state does not necessarily mean that we found the optimal solution. So the resulting planner, it has a cool name, I think, MAD A star, is the first cost optimal privacy preserving multi-agent planner. You can hear about it more in the talk I'm giving tomorrow. So the cost optimal planner was actually an enabling technology for us to start exploring selfish agents. And when I say selfish agents, these are agents that want to maximize their utility. And this MAD A star, this cost optimal algorithm, was actually the enabling technology for a distributed implementation of Vickrey-Clark-Groves mechanism for the setting of multi-agent planning. And the nice contribution here is that we showed that using this mechanism does not incur high computational overhead. Actually, it's linear it adds linear complexity. So selfishness of agents can be dealt with practically. And now to revisit the high-level goals I mentioned, we showed scalable methods for satisficing and cost-optimal solutions. We went beyond cooperative agents to self-interested agents, and we showed how to work with that. And I think that we had a nice contribution in putting the multi-agent planning on the ICAPS community's radar. Of course, along with the DMAP community, which did a great job in pushing this workshop for the past 3 years. And you can even see the number of submissions of multi-agent planning papers. We had, I think, the highest acceptance rate, 67%. Yeah, so that's great. And this talk would not be complete without acknowledging all the people that helped me get through this. Ronan, of course, for his he's been my mentor and advisor since I was an undergrad. So probably nothing would have happened unless he told me come work on a project 7 years ago. The planning community, which I think is the greatest research community on earth, but I don't know too many, so the DMAP community, which really helped push multi-agent planning to ICAPS, and I think we've done a very nice job in this. My great office mates for the coffee breaks, family for the support, both financial and otherwise, and my wife and daughter, I love you very much. Thank you.